Radiation and penetrating power. We've seen that radioactivity is a consequence of the relative instability of heavy nuclei, and we've seen that they can decompose by the alternative emission of alpha and beta radiation, so that uranium can eventually become lead. The main emission is of alpha particles, alpha radiation. These consist of 2 protons and 2 neutrons, essentially like a helium atom. And these are expelled because, as I explained, the heavy nuclei have so many protons in the nucleus that to gain stability they need to offload these, and that's what happens. In between the alpha emissions, there are also emissions of beta radiation. And beta radiation consists of high energy electrons which are expelled from the nucleus when disintegration occurs. So if we remember the diagram showing decay from uranium down to lead, there were a series of downward steps and upward steps. The net passage was downward as the atomic weight went down from 92 to 80. But there were some upward steps. These upward steps correspond to the emission of beta particles, these high-speed electrons. Well, if the particle loses a negative charge, it effectively gains a positive charge. And so it will then move up one on the periodic table before a further alpha disintegration takes it down. Now, if we are considering people working in the nuclear power industry, clearly they will be exposed to various types of atomic radiation, and the purpose of this little talk is to quickly review these and to look at their relative penetrating power. One of the first radiation workers was a Polish lady, Maria Skłodowska. She married Pierre Curie in France and became known universally as Marie Curie. And she received the first Nobel Prize for the extraction of a few kilograms of the element radium from 2 tons of pitchblende ore. So she had somebody deliver a huge pile of pitchblende ore, which she then systematically, over a period of a couple of years, rendered down and put through a chemical extraction process to produce the element radium. Radium is radioactive, and of course in doing this she was shoveling this stuff into buckets and carrying it into the lab and handling it on a daily basis. It was radioactive. Not highly radioactive, but radioactive. And of course over those 2 years she accrued an amount of radiation in her body, which ultimately led to her death in the 60s of leukemia, I think. And many of the early workers in radioactive studies suffered physical damage to their hands and their bodies through handling these materials. They were completely unaware of the hazards. Now, of course, now we know about these hazards, and we've also isolated the different types of radiation to which anyone who works in this field can be exposed. Now, as there are 5 types. There's alpha radiation, beta radiation, there's gamma radiation, there's X radiation, and neutron radiation. So we'll look at these separately and also assess their penetrating power. The first kind is alpha radiation. This is what is emitted when elements undergo radioactive decay, and an alpha particle, as I've said, consists of 2 protons and 2 neutrons. If one of those were to enter your body and get into, say, a carbon atom in your body structure somewhere, the acquisition of that alpha particle could turn the carbon atom into an oxygen atom. So the chemistry of the structures that make up your body could be altered with health consequences. So alpha radiation is damaging, but the particles are quite large, and it's pretty easy to shield yourself against alpha particles. For example, a simple layer of paper or cardboard will shield you from alpha radiation. They're not very penetrating. So that's alpha radiation. Beta radiation, these are the high-speed electrons emitted from the nucleus when disintegration happens. Now these are travelling fast. They are more penetrating, and if they can get, I don't know, sort of 10 millimeters into your body, and they can cause what are called beta burns. So you need to guard against exposure to beta radiation. They can cause damage to your skin and the surface of your body. So that's alpha and beta radiation. Gamma rays are a form of short wavelength electromagnetic radiation, like light rays, only very much more reduced wavelength, very, very tiny wavelengths. And the general characteristics of radiation is that the shorter the wavelength, the more penetrating it is. The longest kinds of waves are radio waves, and they can have wavelengths up to 1 kilometre or more. And of course we know that they will bounce off metal structures. That's how radar works. But they won't damage anybody if you can stand in a beam of radio waves. They will do you no damage whatsoever. But gamma rays are very short wavelength, very penetrating, and we need to guard against soaking up too much of this kind of radiation. X-rays are another form of short wavelength radiation, which can be produced when metals are bombarded, and again they're short wavelengths, very penetrating. They can do damage. On the other hand, they can be used in medicine in a benign way. You can X-ray somebody's limb if you suspect a broken bone, and they will show up the nature and position exactly of the fracture, so you can get it set and the damage repaired. So X-rays can be used beneficially. The other type of radiation I mentioned is neutron radiation. Now, I explained that when an atom undergoes fission, the nucleus splits into two, and neutrons are emitted, fast neutrons are emitted. Now, the thing with nuclear fission is the same, exactly the same two nuclei aren't always produced every time fission occurs. We can think of fission as being a bit more like the start of a game of snooker, when the first player fires the cue ball at the pack of 15 reds to break them up. And anybody who's ever watched a lot of snooker knows that each time the cue ball hits the reds, they break up in quite a different way. They can move a small distance or a large distance, and they go all over the place. You can never predict exactly what's going to happen, and the same splitting never occurs twice. Well, in nuclear fission, this is what tends to happen. Hahn and Strassmann obtained barium and krypton, but you don't always get barium and krypton. You get two nuclei whose combined weight is 92, and one is always certainly heavier than the other, but it isn't always barium and krypton. And similarly, when they split, you can produce 2, 3, 4 neutrons. You never get exactly the same number. On average, in fission, we find that we get about 2.5 neutrons per fission. So that what that means is often it's either 2 or 3 neutrons that are produced. Now, these neutrons are produced by fission. While they can be very damaging, because each neutron has a mass of 1, and it could damage internal body structures, the number of occasions when nuclear energy workers can be exposed to neutron radiation is very, very small. It's a very rare event that anybody would be exposed to this kind of radiation. So it's not something we normally have to worry too much about. We normally handle it by shielding our reactor with materials which will absorb radiation and protect the people working round about. So we've got these three forms of radiation: alpha, beta and gamma, and then we've got X-rays and neutron radiation. Those are the three. In terms of relative penetrating power, alpha is the least penetrating, beta is slightly more penetrating, and gamma is the most penetrating kind of radiation. So if we're going to shield against these, it's very easy to shield against alpha. We need a bit more protection against beta, and against gamma radiation we do need to take extensive precautions because of the penetrating nature of this particular type of radiation. So those are the relative hazards. There's a little diagram I show to compare alpha, beta and gamma, showing the relative penetrating powers of these three types. That diagram, if you like, can conclude this little presentation.